Thank you for inviting me here today. This is one of the few talks at this conference that won't deal specifically with thin films, but with bulk material. Charlie Rees gave us a good idea of blue sky dreams of what is possible with accelerator cavity materials. Sven gave us an idea of state-of-the-art and ongoing developments at Darmstadt. And what I'll talk about today is a capability which should reach an industrial opportunity within the next 2 to 3 years. I've been working on seamless cavities now under DOE sponsorship since 2004 under SBIR money, and that's expired, and I'm now in what's called phase 3 of SBIR, where money comes from outside sources. And I've been fortunate that both Jefferson Lab and Fermi Lab have been interested in continuing support in this, and I've also had the collaboration of Waldemar Singer at DESY, and today I'll present some of his work and my work on seamless cavities produced by hydroforming. The reason we want to use seamless cavities comes from problems in welding of the standard production method. Standard production of niobium cavities from sheet is to deep draw half cells, weld them together, and for an L.L.C. 9-cell cavity, that means at least 17 welds in just producing the cavity before the in-groups are added. And whenever you melt niobium, even in a high vacuum, you're inviting problems with impurities. In addition to that, there are issues with pits associated with HAZ, which have caused a lot of cavities to be rejected. I don't know the specific percentages, but of the L.C. cavities that have been manufactured with a target accelerating gradient of 30 to 35 megavolts per meter, quite a large number have failed in the 12 to 15 megahertz region due to thermal quenching associated with pits. And this might have to do with contamination. It might have to do with other problems associated with recrystallization near the weld. The weld itself is a problem in that it's not smooth and might contribute to magnetic field enhancement at the equator. The approach here, we've used really two approaches. In the work at DESY, after trying a variety of spinning and drawing methods, they chose a method of producing tubes from sheet by spinning or deep drawing, and used those after flow forming to provide the tube for hydroforming. Their work with extrusions were not adequate due to large grain size. The difficulty with using tube that's produced by the deep drawing method, for instance, is that the total length of the tube is limited by the width of the sheet. There's only a certain length of material you can produce in a rolling mill, and tubes of great length with uniform microstructures haven't been produced. One other issue is that in the deep drawing or the spinning method of tube from a flat material, the properties are directional because of the directional properties of the rolled material, and that causes a problem in hydroforming where you'd rather have axisymmetric properties. Our approach at Black Laboratories and working with ATI Wah Chang was to produce a fine-grained billet initially by heavy working of the billet and recrystallize it and use that as a feedstock for an extrusion process. For both of these processes, the tubes were produced and necked by spinning at DESY to produce the iris regions of the cavity, and then expanded by hydroforming. The dimensions chosen here were for the L.C. geometry of approximately 200 millimeter diameter of the equator region. The two methods of tube manufacture used by DESY involve spinning and deep drawing. The spinning method is to take a sheet and wrap it around the mandrel by spinning the support and then applying an external pressure by wheel. In deep drawing, this sheet is pushed through a die into a tube shape. The irises are produced at DESY by a necking process using spinning, or what they call profile ring spinning. The difference between that and other types of spinning, instead of using a small wheel on the outside, a large wheel in this mechanism here is used to apply pressure, and it's moved in both this direction towards the axis of the tube and in and out of the plane of the paper to provide the profile shape of the iris. After the irises are produced on the tube, it's then placed in a hydroforming device. This particular one at DESY was manufactured in Russia and modified at DESY, and uses a hydraulic system and with oil and a water hydraulic system. The irises are placed at a larger distance than they are in the final product, and moving dies are used to push the irises together as the interior of the tube is expanded. You can see some copper pieces here, and copper is the method of choice for experiments because it's a lot cheaper than niobium. And the hydraulic system, oil hydraulic, is used to press these dies together, and they're expanded inside the aluminum dies shown here. The best result so far from the DESY work is shown here in its welding stand, I think, at Xanon, and was a 9-cell cavity which was able to reach 30 megavolts per meter accelerating gradient after electropolishing, I think. The method we chose, using extrusion instead of spinning or deep drawing for the tube, the intention was to give us a long tube with uniform properties, which can be done with the extrusion, providing we're able to maintain a fine structure through the extrusion. A fine structure and also a crystallographically weak texture so that it gives us uniform properties. To do that, we spent a lot of effort on looking at the effects of severe processing of the bulk material and recrystallization processing, and produced a fine uniform billet. I'll just show you a little bit of the microstructure of the different methods we tried. Method on the left gave us an extremely fine interior, but after crystallization, this was in a small billet diameter of 50 millimeters, and the structure coarsened and also showed texture banding here, which happens in niobium under some circumstances of severe deformation. The second process here is the one we ended up choosing and showed the most uniform structure, and a third process also showed a non-uniform structure. Another indication here that this was the most useful, and this is something we rely on a lot to project the stability of the fine-grained structure, and that is that the grain boundary angles showed a nice distribution. Instead of going more towards the low angle boundary side here, the boundaries here in this section were peaked towards the high angle and showed quite close to random distribution. We also looked at the crystallographic texture intensity, and process B here had from the outside, the middle, and halfway between had the most uniform intensity of texture. When we produced the tube,